Hey everyone, thank you for tuning in to a demo on fine-tuning a residual network. Today we'll talk about, as the name suggests, residual networks, which are a type of neural network where we have skipped connections or residual connections. And we'll also discuss a problem in computer science. Maybe I'll write this out. So a problem that we often have is that the models that work are very, very large, hundreds of millions or even billions of parameters at this point. And even if it's not that, if it's like millions or tens of millions, it can still be very difficult to tune and to train. So the models that work are very, very large, and these are expensive to train. So what do we do when we have two situations? One is that we don't have much data. So maybe it's difficult to come by data because we are working with a particular type of data set that needs to be hand labeled. Maybe it's that we just don't have much of a budget to do it. So what should we do in a setting when we don't have much data and like a very large model needs this much data or else it'll completely overfit and it won't learn anything that generalizes. And the other setting that we are interested in is that we don't have a budget to train from scratch. Maybe this is because it's very expensive to train from scratch, or we don't want to spend the computational resources to do that. So what should we do? One solution is to, in the small data setting, is to one, start with a deep network architecture, which is initialized with pre-trained weights. When I say pre-trained, that just means that someone else has trained these weights and they've been kind enough to upload them onto the internet or otherwise make them accessible to us. And then the second step of this is that we will fine-tune the network weights on the data set. It might be a small data set that we have access to onto a small training data set. So that's exactly what we're going to do today. The particular type of network that we're going to be interested in is a residual network. So I'll just put an image of what that looks like here. Let's see if this works. Yes, okay. So this is a residual network. We're used to the normal picture on the left, which is we pass in some input, or sorry, the picture is on the right, but we're used to everything except the skipped connection. We're used to passing in some input X, applying it to some kind of layer, a convolutional layer or a linear layer. We are familiar with both at this point. We get some output F of X. And we say F of X is both this layer and that layer applied to the input X. And we're used to what that would look like. But with a residual connection, we add X as if it were skipping these two layers. And so the value of what's being passed through the network at this point is now F of X as if it was passed through that, which it was, plus X. And this is a residual connection. We'll talk about this in a bit, but in the back of your mind, I want you to be thinking about why this would be useful. Why would we want to have skipped connections like this in a network? Okay, so while you're thinking of that, let's start some coding. As normal, we're going to load a bunch of libraries. And excellent. The first thing that we're going to do is imagine that we have our own special data set. The special data set will actually be provided to us, and it'll be some pictures of cats and dogs, but that's honestly not that important. So as long as you copy the file structure, you can use anything. I'll put the link right here. And this is also, of course, accessible through, so you have access to this demo, and you can click on the link, and the link is in that demo on the version that's on GitHub. This is where we're going to get our data. It's in the zipped folder. You can click on this download button over here, and they'll download this zipped file. If we want to open this, you can just open it on your computer and unzip it. Then, so that we can have access to this on Collab, we're just going to go to your normal Drive folder, and you'll have the option to upload a folder. This is what it'll look like. Once you've unzipped it, it's a data folder, and you can click upload. I won't because I already did it. Once it's uploaded, it'll be in a file structure called train and val. This is training data, and this is validation data. And you can see that we have 30 pictures of dogs that are very cute. And then in the training data, and we also have 30 pictures of cats that are very cute. So this is we're gonna pretend that cats and dogs are very uncommon to come by. That's very much not the case. There are pictures of them all over the place. But we'll pretend that we don't have much data, this is it. And we want to fine tune a network on our data set. This is the data set that we'll use, but if you copy that file structure, you can honestly use whatever different data set that you want. Okay, so once you've done that and you've uploaded it to your Google Drive, you can access it by using let me get this right. By using a library that Google provides, and you just say this by mounting this. This is the path to your normal Drive folder. When you open Google Drive, this is what it's called. And then when you run this, you might be prompted to connect this to your Google Drive, in which case a screen will open up and you'll have to go through a few prompts to sign in and give access to Google Drive. Once you've done that, this will load. And now we can load this data into our Collab notebook. Remember, the thing that we normally do is we take in some data of some size, we convert the size, we crop it, we turn it into a tensor, and often we're going to normalize our data. This is just a scaling process that we do, which makes our data more similar to each other, which helps with the learning process. So all of this is going to go into a data transform. I'll call this dset transform here. And the thing that we're going to do is compose several operations. The first operation is that we'll resize the image to be 256 by 256. Then we'll crop it, resize it to 224. We'll convert the image to a tensor so that we can pass it through a network, and then we'll do this renormalization process. These are values that are I believe, the mean and standard deviation across each one of the different RGB values. And we're just setting this because I think this is the common value that's used when training the residual network. And we want to be as close to that as possible when we pass in our own data set. Okay, so we've defined this data set transform. We're going to create the data sets. So I'll say dsets equals this. I'll put it in a dictionary to make it short and clever. And we can get it using this handy datasets.image folder function. We'll get, and the path to this is content/drive/my drive/ wherever it is. In my case, that's just in the data folder. And you're calling it x, where x is, these are the two parameters that we're passing in. So we're transforming it. And then this is for x that's either it has to be the names of the folder. So this is train and val. Cool. Okay, so we run this and it should run correctly. We now have a data set, so we can look at one of these. We can look at dsets train, and we get a data set folder. We're told there are 60 images in there, and we're told where it is. Once we have a data set, we want to convert it into a data loader, which will be very easy for us to use. We'll do a very similar thing. We'll just use the torch utils data loader function to load the particular data set with a batch size equal to 16, and then we're going to shuffle through all of this. And again, this is for X in train val. Okay, cool. So let's take a look at, so we're going to create the data loader. Let's take a look at some of what's going on here. So we're going to inspect our data set. We can do this by getting a batch out of our data loader. So the data loaders that we're interested in, let's call it the training data loader. We can get the next value of this if we turn this into an iterable. If we do that, we get two very large objects, two tensors. Generally speaking, this is pairs of data. In our case, it's images and labels. So if we print images.shape and labels.shape, it should be quite familiar to us. So for example, we know based on this resizing that we're going to have, it's going to be 224 by 224, and these are color images. So the size of this should be 3 by 224 by 224. We also know that the batch size is 16. So when we run this, the images shape should be 16 by 3 by 224 by 224. And then the labels should be 16, should be size 16. And that's because they're going to contain values of 0 or 1, corresponding to whether the image, the corresponding image is a cat or a dog. Now that we've looked at this, or we understand the dimensions of the data, let's actually plot this. So I'll write a quick function, which will take in images, labels, a number of rows, and a number of columns. And we're going to create some figures and axes to plot this. This is fairly standard, but very helpful to do when you want to understand what's going on with your data. I'll have this IDX index for iterating through it. I'll say for I in range and rows, for J in range and columns. We'll define our axis as the ith j thing in this object that we created, and then we'll run imshow on the image at the corresponding index. Remember, because of some annoying disagreement in how we should write the dimensions of images, Tensor wants them in channel height width format, but when we plot them, they need to be in height width channel format. So we just need to permute the images here, and then here, let's set the title so we can see how well our model is doing. So I'll get out the corresponding labels index, and if I didn't call item on this, this would be gross and appear as a tensor, so this just turns it into a scalar number. I'll turn off the axis because we don't care about the x and y axis here. And then finally, we need to iterate through the indices, and I'll call plot.show here. So we're going to call this new nice plot images function on the images and labels that we just defined. When we do this, we should get some nice pictures of cats and dogs, and it looks like 0 corresponds to cats and 1 corresponds to dogs. Notice that all of these images are unfortunately colored. That's because we did a rescaling when we did this transform. So when we did this normalization operation up here, that renormalized them to make it look like colors that were easier or were within the distribution of the images that this model is trained on, but they're not within the distribution of images that we're familiar with. So that's why it looks a little bit funky here. Okay, so now that we understand our data and we visualized it, what's not to love? It's very cute cats and dogs. We're now going to load a pre-trained ResNet model. ResNet here, is just a residual network. So we'll load it and poke around at it a little bit. Luckily, this is saved online and it's very easy for us to load. So we can just write ResNet 34, and we want the pre-trained version of this. That just means someone else has already trained it. That loaded very quickly. It looks like we're in luck. We can print this model, but this output is a little bit difficult to read. Instead, we'll use the same method we did last time, which is called summary on this model. And then remember, because this is a convolutional layer, we need to specify the size of the input image, because unlike linear layers, the input size is not fixed in advance. Our input size here is the dimension of the image, which as we saw was 3 by 224 by 224. If we call this, we see that this model is very, 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 very large. Lots of convolutional layers, normalization layers, pooling, ReLUs, everything that you want. And over time, it starts out quite large. It's 112 by 112, then becomes 56 by 56, all the way down to 7 by 7. And the thing that we're outputting at the very end is that we're going from this representation of this image to a 1,000-dimensional vector. The reason that this is 1,000-dimensional is because there are 1,000 labels on the data set that this was trained on. And the data set that this was trained on was very large, millions and millions of images. And because the data set is so large and is trained for so long, we expect this model to have learned something very deep about what's going on with that data set. And that's why we want to use this model when we're, instead of training something else from scratch, we've done a lot of work to get weights which are quite useful, and we want to be able to use that for our particular task. The first problem that we have, though, is that the output of this model is 1,000-dimensional, and the output of the model that we want is just 2-dimensional. We want to be able to output whether it's a cat or a dog. Before we run into that, though, let's just take a look at the number of parameters here. It's 21 million parameters, which is absolutely ginormous. So there are tons and tons of parameters in this model, and it took a very long time to run. Okay, right. So the problem that we have is that we want to have 2 outputs here, and this output is 1,000. So if we print our model again, we can, and we go to the very end, we can look at the name of this last block, and that last block was just called FC. Okay, so the thing that we're going to do is replace that last layer with a new layer, which is just a linear layer with output 2-dimensional. The number, but we need to make sure we get the number of features right. It looks like that's 512, but we can check that. We can check model.fc, that's the name of the last thing, and look at the number of in features. When we do this, this is 512, which lines up with our understanding right there. So we will rename this model FC thing to be a linear layer, which has num features as input and 2 as output. So what we just did is we replaced this last layer with a new layer, which outputs a 2-dimensional object, and that 2-dimensional object we will interpret as either cat or dog. So now if we call summary on the model, and we suppose that we pass in a 3 by 224 by 224 image, we'll again get something that's very large, but at the very end, our output is now 2-dimensional. So we've changed the dimension of what we're outputting in our model. And that's very good because we want to just output whether it's a cat or a dog. Okay, before we start the training process, let's see if our model can take our images as input. And we'll just do this in the evaluation phase. We'll say that we're evaluating our model. This just means that we're no longer keeping track of the gradient, which slightly speeds things up. And we're going to count the number of correct labels that we get. We'll iterate through our data. So for batch index in inputs labels in enumerate. So we'll go through our data loaders, or our data loader, which we access by saying val. This tells us, enumerate just gives us the thing that we're iterating over and a corresponding index. Maybe we actually don't need this. We can just say our outputs equals the model applied to the inputs, and then our predictions are just the maximum value of the outputs along the first axis. And then the corrects, we'll just add 1 every time the predictions are equal to the actual labels. And at the end, we're going to print the number of things that we've gotten correct divided by the length of this data loader, which is the number of images we have in our validation set. And this should be data loaders. Okay. So we're just doing an evaluation phase right here. Oh, this is taking a second. No, that's fine. Okay. It looks like we got an accuracy of 0.4583, which is generally close to 0.5. So I would say that we would accept this. Let's use our handy function to plot what we're getting here. First, let's look at the dimension of our images. This is still, sorry, we're calling it inputs here. So it's inputs.shape. This is 8 by 324 by 224. This is because most of the batches are 16 size, except the very last one, which is what we're defined on because we finished this for loop, is 8-dimensional. So I'll call plot images. We are calling it inputs and predictions. And because it's 8-dimensional, I'll just say that there are 2 rows and still 4 columns. When we run this, it looks like it's just always outputting 1, no matter what the image is, which is quite reasonable because we randomly initialize the weights in this new layer that we added. Okay, let's now do some training process here. I'm not going to write out all this code because it's quite standard, but I will explain it. And if you have questions about it, I really encourage you to ask. This is the first step of our recipe. This is the loss, or sorry, the second. The model is the first step. This is our loss function. This is our optimizer, how we go about updating it. I'm going to create a dictionary which will keep track of the training accuracy, or the training and validation loss, and the training and validation accuracy. We're using stochastic gradient descent with a momentum parameter and a small learning rate. We use a small learning rate when our model is quite large, which it is in this case. If we look at model.parameters, which is the thing that we're calling this on, this is a generator object. Can we take the length of it? No, okay, never mind. We won't take the length of that, but I think this is all of the parameters in the model. So we're going to be updating all of them, and this will take a little bit of time. So I'm going to just copy and paste the training code that we're going to use, and I'll walk through it as it runs. So we have 2 different phases, the training and validation phase. We will set our model to a training mode, which means we'll keep track of the gradient if we're in the training phase. If not, we'll set it to evaluation mode, which just means we won't keep track of it. We're going to keep track of our loss, and we'll keep track of our corrects. We'll use the same enumerate trick we used earlier, where we iterate through whatever this object is. That goes here, and then the index of our iteration goes into batch index. We'll always zero out the gradient before we start computing anything. And then we'll set this. This is a clever way of checking whether we're in the training phase. If we are in the training phase, then we'll keep track of the gradient. If we're in the validation phase, then we won't keep track of the gradient. We're going to apply our model to our inputs, which are our batch of images here. And we'll get out predictions. The predictions are just the max operation applied to the outputs objects. So it's whichever dimension is larger, that'll be our prediction. Our loss is directly applied to the outputs of this model, and this loss is cross-entropy loss that we defined above. And then if we're in the training phase, if phase equals train, we'll take a step backward and we'll update our weights by doing optimizer.step. We'll also want to keep track of our loss and our accuracy. So our current loss will get our loss.item. This just takes it out of the tensor form and puts it in a normal scalar that we're used to in Python. We're going to multiply this by the size of the number of images that we have, and then we'll update the number of corrects that we have, which is how many times our predictions are equal to the actual labels. We'll save these things for plotting. This should be plotting. That's funny. And we'll just normalize by the size of our data loader. And then we'll print out where we are in this epoch, the phase that we're in, what our loss is, and what our accuracy is. So it looks like in the training phase, we start off with high loss and accuracy around 55%, which is exactly what we expected and saw in the beginning, because it was just random guessing. Over time, this very, very quickly increases until we're getting 100% accuracy on the validation set and near 100% accuracy on the training data set. We can plot the things that we've kept track of over time. So we're going to plot the save accuracy object, and we're going to also plot our validation and our training accuracy, and we'll have the legend train validation. And to be fancy, let's give it a title. Accuracy, let's be accurate with this. And if we show this, we'll see exactly these values change over time. They got better and better. It looks like we just learned very quickly. Interestingly, the validation accuracy is higher than the training accuracy. One reason this may be the case is because we're doing the training phase first and then the validation phase. So whatever we learned in the training phase, we picked up in the validation phase. And you can kind of see this. Initially, these are quite low, but the validation value is higher. And after one step of this iteration, we're already higher than we were at the previous time step for the validation phase. But this isn't true afterwards. So it looks like when we're done training, for some reason, we're doing better on the validation set than we are on the actual training set. Whenever this happens, this is indicative that we learned something that generalizes very well. So in this case, we actually learned to be able to discern cats from dogs. And this should be something that is very surprising to you because we didn't train this for that long, and we only had very few images and very few examples of it. So just to convince you that this actually worked successfully, let's use our helpful plot images function on our inputs and our predictions. I think it's the last one that we're looking at again. So I'll say n rows equals 2, the number of columns is 4. And when we plot this, it looks like we learned this exactly. So remember in our data set, 0 were cats and the dogs corresponded to 1. And it looks like that's exactly what our function has learned very, very quickly. Oh, that was here. Okay. Right. So it looks like this has learned very, very well. And you may be tempted to say that this is perhaps in part because we're using a very large model that is pre-trained, but also there's a component that we haven't talked about yet, which is that residual connections and residual networks have a very special property. So let's discuss this briefly and then we'll be done. So why residual connections? So remember, this is the question I wanted you to have in the back of your mind as we were going through this process. We started with an image, sorry, I'll scroll all the way up to the top, which is what a residual connection is. We pass our data through our normal function, our normal network, but at the very end, or several times throughout, we add something from a previous layer to the next layer. Now, there are kind of two commonly accepted reasons why we might want to do this. One reason is that maybe the data or representation we have at this layer is already very good. Maybe after 2 or 3 or 10 layers, we've extracted something important out of the input to our model. And if we were to just pass that data through a bunch of more layers, we may lose what's so important about that information. You can probably intuit this very easily if you think about the initial starting state of the model. Maybe the model learns initially how to extract useful information, but it hasn't yet learned higher weight values up here. So if we pass something that's useful through a bunch of randomly initialized weight layers, we may lose the information that's useful. So in some sense, by adding this residual connection, we allow the model to keep a memory of what was so useful before without having to pass it through or learn how to pass it through these layers. Something else, another commonly accepted reasons why residual connections are so successful, or residual networks are so successful, is because if we had a normal layer and it was very, very deep, we didn't have any residual connections like this, the gradient updates with respect to the weights all the way down here would be very, very small. because that had like a relatively small impact that was probably averaged out across all these different layers on the final output value. But because we have a residual connection like this, we have some way that the output is directly influenced by the weights at this level that are all the way back here. Because that's the case, we're maybe more likely to update these values in an interesting way, and we can maybe learn the information or weights at this level more efficiently and more quickly. Okay, so I'll write these down, but you can also find observations and explanations like this online. So the first reason that residual connections are useful is that residual connections allow important information to go through the network without having to pass through many weights. The second reason is that we have more direct gradients and updates to learn lower level weights. I'm just saying lower level to mean they're towards the bottom of the network, to learn lower level weights more efficiently and quickly. Okay, so how do we know that residual connections are effective and work? I'm going to put two images here, and these are images of a lost landscape. Okay, cool. So this, I actually love these images. So the thing on the left is a VGG56 network. The name isn't so important, but the very interesting thing, so this is a loss landscape. This is the loss value as we change parameters in the parameter space. So if we start here, it looks like we have a very good loss, but if we move in this direction, it increases. And if we move over here, it increases very drastically and it's very, very sharp. I'll describe in a second how we get images like this. But the thing that I find super interesting is that the network on the left is the same as the network on the right, except the only difference is that there are residual connections on the network on the right. So intuitively, it seems like by simply adding residual connections and making no other changes, we've made the loss landscape smoother. Because it's smoother, it seems like we can learn on this landscape more easily. Of course, when you learn about gradient descent in practice, we assume that we have a nice convex optimization problem, which is definitely not exactly the thing that we have on the right, but is much closer to the thing we have on the right than what we would have on the left. So really residual connections are important, and you can see this effect on these lost landscapes. I want to describe to you how someone created these images, because I think it's quite interesting. So these, of course, the challenge, right, is that the number of parameters on these networks and definitely on the ResNet networks that we worked with are quite large, and we have no hope of visualizing anything in 4-dimensional space, much less 21-dimensional space. So the trick here is that these plots are acquired by taking the trained parameters. I'm going to call these trained parameters theta star. Actually, instead of typing this out, I'm just going to copy it and I'll explain it. And I think that'll be better for us. Okay, so these plots are acquired by taking the trained parameters theta star, which are an RD dimensional space where D is the number of parameters we have, and we perturb them in two random directions, delta and eta, which are in the same dimensional space. So we have a vector set theta star, and or a vector theta star, and we randomly initialize two other vectors, delta and eta. And these other vectors are pointing in some other random directions. And then the thing that we're going to plot is a function f of xy defined on x and y, which are scalar values. That's the reason that we can plot this thing. And what is this? Well, f of xy is our loss function defined on theta star, the trained parameters, plus a little value x times the direction delta plus our scalar value y times the direction eta. So the reason that both of these plots are at the lowest level in the center is because that's where x and y are 0, and we just recover L of theta star. So it looks like the loss is the lowest on the trained parameters, which is exactly what makes sense to us. And if we increase x, we move in the x direction here, then we go out of this local minima. If we go in the y direction, we also go out of this local minima. And this plot was very computationally intensive to create, but it's quite interesting to look at, and it's really just as we vary how much of a random vector in each one of these directions, how much does the loss function change? This phenomena, I'll put two links here. And you can acquire these links by simply looking at the GitHub version of this demo where everything is written out nicely. The phenomena is described more detail in this blog post, which describes this process and gives some intuition about it. And then I think this is very, very fun. And Karthik, who did the demos last year, found this wonderful interactive visualization tool where we can actually look at one of these loss functions and play around with it. And you can see, so this, it looks like, is the model ResNet 56 with no short. No short here means no connections. And then we can look at ResNet 56 with short connections in it. Here I've plotted both of them, which makes it difficult to see, but if we remove that, we now have the exact same network, but with residual connections, and the loss function, or loss landscape, looks much, much smoother. So really the reason behind this is I think there are several interesting things going on here. One is that this is a method to visualize loss or loss landscape, and I think that is a quite helpful tool and gives insight in this case to residual connections. Another thing that's going on is that residual connections are quite helpful, and they make this network much more powerful. And you'll see ResNet is a network that is now quite old, but many of the modern networks, such as UNets, which are quite helpful in processes like Stable Diffusion or other ways of generating images from text, they also use skipped connections like this, perhaps in a more principled way. So that's a very clever insight. And finally, the big thing that we did today is we took a pre-trained model and we fine-tuned it on our small data set, and we saw that we were able to very quickly and efficiently learn what was going on. And the reason we did that is we preserved most of the weights of this model, except we just took the last level and we replaced it with a new level, which we pre-trained to get the type of output that we wanted. So thanks so much for making it through this demo. And if you haven't come yet in person, I'd love to meet you and get to know you better. The demo itself is posted. All of this code with much better explanations are written out in this link. And if you have any questions, please feel free to post on the discussion format. Thank you very much.